Good morning, guys. Let me go over the calendar for this week. There's some adjustments here. So we covered 5.2, 5.4. These kind of build on each other as we go to today's. We're just learning another set of rules, but a lot of it is just use substitution and either long division or synthetic division. Now on the quiz, you can choose either to use long division or synthetic division. I'll give you a problem that can be solved both ways. Okay. Your quiz will just be over what we covered last week and today. Okay. So the quiz was initially Wednesday. We're gonna flip-flop the days with the next topic, differential equations. So we're covering differential equations tomorrow, not on Thursday's quiz. Not on Thursday's quiz. It's just 5.2, 5.4, and 5.5. We'll be done with new material today. So tomorrow, if we can get through this topic early, I can start quiz review early. Quiz review Wednesday, quiz on Thursday. So make that adjustment in your calendar. Any questions? So for the 6.3 homework, I won't make that due until Friday. So I'm not gonna, after I check homework tomorrow for tonight's, we'll just focus on quiz review. So homework for 6.3 won't be due until Friday, and then we should be back on schedule. Okay. So once we get into 6.3, that's going to be like the last major topic for this unit. I mean, we have a little bit more integral rules to learn, but then we'll have a few days, and then we'll have a chapter 5-6 test, not next week, but the week after, and then we start our final unit. So we'll be done with our final unit by mid-March, and then we start AP review after that. Okay, a month and a half to do AP review. Okay, so page 5. Let's run through the rules that we know, as well as ones that we need to be responsible for the quiz. So let me start up here because I left these ones off, but these are ones from 5.2. So the derivative of natural log of u is u prime over u. Okay. We know the integral of 1 over u du. This is the one case that power rule is not able to handle, because if you try power rule, you'll get u to the 0 over 0, and we know we can't have 0 in the denominator. So natural log absolute value of u plus c. Okay, so we need to know the derivative and the integral rule. We know the derivatives already. We're just practiced the new one last Wednesday. And then the nice thing about e to the u is that it's basically itself derivative and antiderivative. So e to the u times u prime. And then for the integral, it's just e to the u plus c. So that's nice about e to the u. If you forget the rule, it's really just itself. So now today, we're going to tack on this a to the u rule. Okay. Now these both fall under exponential functions. Okay, an exponential function is when you have a constant as the base, raised to a variable. Okay? A constant raised to a variable. So it could be 2 to the x, e to the x, 5 to the x, 6 to the x. We need to be able to recognize exponential functions and not mistake them for power rule or a variable raised to a variable, a constant raised to a variable. We have a name for that. It's called exponential function. So we have two variations of them. One is for e. So if we have base e, we have a special rule for that. It comes out very clean. But if I have other bases like base 2 or base 3 or base 5, we categorize them all as a to the u. So last semester, we learned a to the u, very similar to e to the u. It's basically its function itself times the exponent's derivative, but there's a little bit of conversion with natural log that has to happen. So we say natural log of a times a to the u times u prime. A quick example here, if I ask for the derivative of 2 to the x squared, then it's just natural log of 2 times 2 to the x squared times 2x. So that's all review. So now we're going backwards. So the antiderivative, we're starting with the derivative and moving to the original function. We know that, well, if I take the antiderivative of a to the u, we ignore that u prime is basically the u. We're going to end up back where? A to the u, right? So not much changes, except we got to deal with what? This natural log of a has to go somewhere, right? So if I take the antiderivative of a to the u, this natural log of a is just going to end up in the denominator with your antiderivative rule. So basically, you're reading your derivative rule backwards. If the derivative of this is this, then the antiderivative of this is back to a to the u. But since we're just taking the antiderivative of a to the u, the natural log of a has to go somewhere. It's going to end up in the denominator of your answer. So the integral of a to the u du is just 1 over natural log of a. It's going to end up in the denominator times a to the u plus c. So largely, exponential functions are nice because the original function shows up in your antiderivative rule, but there's a little bit of carryover with that conversion that has to happen. All right, so let's try number 1. Integral of 2 to the x dx. We have to recognize that this is an exponential function, right? You have a constant 2 raised to a variable of x. So we need to recognize that as an exponential function. Exponential function falls under these categories here. Okay, now this is base 2. Base 2 is not base e. We call it base a because base a represents all the other whole number constants we can think of. Okay. Base 2, base 3, base 5, base 4, base 8. They all follow this rule here. Okay. Is there a need for u substitution? Just x, right? So x is just u, so we can just follow the rule without having to do any worry about leftovers or carryovers. Okay, so we just follow the rule here. 1 over natural log of 2. That's my coefficient times 2 to the x plus c. Now, 1 over natural log of 2 is just a numeric coefficient, so you can leave it here. You can put it in the denominator. I just like to leave it in front, treat it like a numeric value in front. Okay, example 2, integral of 3 to the 4x. Do we recognize this as an exponential function? Yes, right, constant raised to a variable expression. Okay, so this fits nicely with integral of a to the u, but here we have to do what? U substitution, right? That 4x is a little bit large. We have to keep track of that coefficient. Well, there's a leftover from that derivative, so we have to get it into this form. We're going to make it look exactly like this, except the a's will be replaced with 3. Okay. So I'm just going to replace the 4x and the dx. Okay. Solve for dx. Okay, what's left over? Gonna do with that 4. Put it out as 1/4. Can I merge this and make it 3/4? No, okay. This 3 is kind of stuck in that form. Okay, that 3 is not 3 like you would expect from a coefficient. That 3 is stuck inside this exponential function, so it can't merge with other numbers, at least not easily. Okay, so 1/4 comes out. Okay, so this matches nicely with the rule that I want to use. Coefficient is out, perfect match. My A is 3, my U, du. Okay, so now 1/4. Okay, let's follow the rule. What's first? 1 over natural log of 3. So there's quite a bit of numeric coefficient that has to hang out in front times 3 to the u plus c. Okay, so there's our answer, but we have to make a slight change here for our final answer. What's the final piece? Yeah, replace the u back with f4x. Yeah. So I'm just going to merge this together as one fractional coefficient. You can leave it like this if you like. Just replace the u, but I like to do this. But you can put it in the denominator. You can put it in front. You don't need that. You can leave it separate. 1/4 times 1 over natural log of 3. Yeah, but this is how I'm going to present it. So, but as long as all the pieces are there. Okay, number 3. Okay, now this too messy for any one rule to handle. We can't separate it and say, okay, I'll deal with the tangent, then the secant, then the 5. Right, this is all connected here. But do we see how this fits into an exponential function form? Right, I have a constant raised to a variable. What could be our u value that could allow this to clean up to look like this? U is what? What could be our u value? Tangent x, right? And the nice thing about that tangent is it's an exponent. If this is the u value, we're hoping that the derivative will take care of that remaining secant squared. Do you think that derivative will take care of it? Yes, because tangent derivative is secant squared. So we know that if we make those two substitutions, we should be able to come out cleanly to look like the rule that we want to apply. Again, your goal is to make your problem look exactly like the rule you want to use. No coefficients left over. This matches perfectly with this a to the u rule here. Okay, so go through our rule here. 1 over a natural log of 5 times 5 to the u plus c. There's our antiderivative. Now let's bring back our original variable. Okay, problems are looking a little bit more complex here, but let's see if we can look past the messiness and discover how we want to start this problem. Okay, do you see an exponential function hiding in here? Base 7 raised to an exponent. So what could be our u value? Yeah, it's going to be the entire exponent. Okay, now if we ever want to do a u value for the exponent, we can't pick and choose and say, oh, I just want that 3 minus x, because then we're working towards 7 to the u squared, and we don't have a rule for 7 to the u squared. We only have a rule for 7 to the u, or 8 to the u, or 9 to the u. Okay, we don't have a rule for u squared. So it's got to be the entire exponent. This is going to work. It's got to be the entire exponent. Okay, we leave that 3 minus x alone out front. We're hoping that will take care of itself. So I'm just going to make these two substitutions, and once we make those substitutions, we're hoping that this will work out for us. Okay, so u equals 3 minus x quantity squared. Now, what rule is needed for us to find the derivative of this? Chain rule, right? This is outsized derivative times insized derivative. So outsized derivative, the parentheses squared becomes 2 parentheses to the first power times the insized derivative, 3 minus x becomes -1. Okay, I'm gonna leave that parentheses there because I see the 3 minus x, and I want to try to have my derivative look as close to what I'm trying to cancel out. So I'm just going to put the 2 and the negative together, cross multiply. Okay, make my substitutions. That 3 minus x is a good thing to have because we do see a match. We do see something that will work out for us here. All right, does our x variable go away nicely? Yes, but there's a leftover of what? -2. We push that out as -1/2. Once we get past that coefficient, it should match perfectly with the rule that we want to use, which we do, a to the u du. Now we can apply our antiderivative rule. -1/2 stays. There's a conversion that's happened, 1 over natural log of a to the u plus c. And our a is replaced with 7 because 7 is our specific case for this particular problem. Replace the u back in terms of x. Okay, number 5. So here's a general rule of thumb is that the larger your problem, the larger your u value must be, right? Because we can't just let u be a small portion. It may not get our problem down to a simplistic rule that we want to work towards. All right, any guesses as to what our u value could be? We may be involving other rules here. So the exponent is not going to be large enough because we have all this mess in the numerator and denominator. Yeah, the whole denominator. Again, if you're choosing between numerator and denominator, denominator is a good place to start. The nice thing about this denominator is that we see the 7 to the u. We know a to the u's derivative is also going to involve a to the u. So we're hoping that a version of this will show up to cancel out with that one up top. Okay, so I'm going to rewrite the problem here. So as a reminder, this is our first semester here. The derivative for natural log of a is natural log of a times a to the u times u prime. So the derivative is really only going to impact that second term, right? That 5 will just go to a 0. The negative is going to stay, so 0 minus, so minus negative natural log of a times a to the u times u prime. Oops, I didn't copy the question right. There was an x hiding here in the problem. But that x is going to be important. We're going to need that here. Okay, so what's u prime going to be? 4x. Solve for dx. It's really messy derivative, but we need it because we have quite a few things that we're trying to match and pair up. So I'm just going to replace these two pieces, and we're hoping that this derivative will handle a large portion of what still needs to be dealt with. All right, does the exponential function go away here? Does, right? So that's good. What else? Yeah, so that's what's most important, right? Make sure anything involving x has to find its way to go away. But what can we push out in front? Yeah, the 2, the negative natural log of 7, and the 4. I'm gonna push all that out in front. So that gives me 2 and 4 is negative 1/2, negative 1/2, and then the negative natural log of 7, all that goes in the denominator. And now I'm able to get it all cleaned up to something that is recognizable as a rule that we can apply. Okay, so everybody good with how I cleaned up that coefficient here? The 2 and the 4 is 1/2, and then 1/2 and natural log of 7, and a negative. Okay, we know the rule for 1 over u is natural log absolute value of u, so coefficient stays. And then replace the u with what we created at the very beginning of the problem. All right, number 6. What's different about number 6? Yeah, we have bounds, right? But do we work with the bounds to begin with? No, it's the last thing, right? So we pretend like we don't see the bounds and we just handle the in-depth integral. I'm going to rewrite this as 1/3 x. Feels a little bit cleaner. So this is pretty straightforward, right? This is u substitution. This is exponential function, a to the u. What's our u value? Exponent, right? 1/3 x. Okay, 4 to the u times 3 du. This matches pretty nicely. We can push that 3 out in front. Okay, antiderivative rule. A to the u is 1 over natural log of a times a to the u plus c. But we'll leave the plus c out. Okay, replace the u back in terms of x. I'll make this come together here. I'll just make this a little bit cleaner of a coefficient. Okay, so I brought everything back in terms of x. I found the antiderivative. Now I can do what? Now I can work in the bounds, right? Now the bounds feel out of order. Is it okay? Yes, right. We're not trying to read the graph and trying to decide, oh, wait, what's positive, what's negative. You can, but it may not be worth the trouble because you got to keep track of another negative if you do that. So I'm just going to just do whatever they present, and the answer is going to be the answer. Okay, upper bound first. One-third times -12 minus 3 over natural log of 4. 4 to the 1/3 times 6. Now, just to let you know, you don't have to worry about how far you have to clean up, because as long as your answer is a numeric value following definite integrals, then that's sufficient. I'm just going to clean up a little bit more. This is 4 to the -4. So this is fine. I just want no negative exponent in the answer. So you can make that 4 squared. You can leave that 4 squared. I'll put 16 there. Not going to merge. I mean, you could merge it together and, take out a GCF and do common denominator, but that's not required. Okay, go to page 6. The most challenging part of these problems is always this first step, right? Trying to decide what the u value is and trying to decide what rule are you trying to work towards. Okay. So let me write all the major integral rules here, and we can kind of decide what the U value is, because most of these problems are going to be too messy for any one rule to handle. So the four major integral rules that we've seen that are non-trig is you got the natural log rule, you got e to the u, you got power rule, and you have a to the u. So these are related. These are both exponential functions. Power rule is for a variable raised to an exponent numeric value, like, x to the fourth or 5x squared, x to the -4/3, right? That's power rule. Okay, so let's just go through and identify what could be our u value. Okay, what could be our u value, and then we can always go back and I think the hardest part is just that, or the most difficult part is that first step. So look at number 1 here. What could be our u value? Because obviously this is too messy for one rule to handle. Right? We can't expand this, too many terms in the denominator. Okay, what do you guys think? Entire denominator, yep. And what do you think this rule will eventually try to look like? 1 over u, yeah. Right. Everything else is just, following through the steps. Okay, number 2. Well, number 2 here. Obviously, u substitution, right? There's too many terms in the denominator. We can't split this up. Also, what? Also the entire denominator, right? That sign will produce a cosine, which is nice. Again, this will look like 1 over u du. Yes.
Will always be the entire denominator.
If the degree is favorable, yes. And also you can kind of look ahead to see, can you imagine the derivative producing something that matches the numerator? Okay. But we're going to see that's not always the case, but if the denominator looks more complicated than the numerator, then at least I want to eyeball it and at least test it out in my head to see if I can see it working out. Okay, what about number 3 here? The exponent. Yeah, this is e to the u. That u in the exponents should create a derivative that is nicely matching that 2t plus 1, or at least some version of it. That degree will fall to first degree. 5t will become a constant. Okay, how about number 4? What could be a good fit? Denominator, right? That degree should work out nicely. X squared will turn to x, 15x will turn to a constant, the 6 will go away. Should look nicely like that 1 over u. Okay, how about number 5? Parentheses, yeah. I know that x squared is kind of throwing you off, saying how can this produce anything x squared? Well, this is a denominator here, so this becomes 7x to the -1. Derivative is -7x to the -2, so this derivative will produce an x squared once we get it in the correct form. And everything, once everything cleans up, we're hoping this will turn into a what? Actually a trig rule, right? We're hoping this will turn into a cotangent of u du. This is one of the new natural log rules that we'll try to go over during the quiz review. Okay, number 6. This is maybe a little bit different here. Any hints, any clues as to what the u value could be here? Gideon? Inside the root, yeah. This natural log of x, what's nice about that natural log of x? What's the derivative of natural log of x? 1 over x, right? And that 1 over x should match up nicely with that leftover x that we have in the denominator. So this will end up being a power rule once that's all cleaned up. Okay, what about 7? Denominator, yeah. That denominator is much more complicated than the numerator, and it will produce something that will pair up nicely with that numerator. And this will work out to be 1 over u du, because once everything settles, we should get to look at that. Number 8 is a little messier. I'll leave that alone for now. Number 9. This is different here. Okay. Typically, we don't do u substitution if the numerator has a higher degree. This is a method we talked about last time. It's a synthetic or long division, okay? Because anytime your degree is higher and I can't split up like I would like with power rule, this is one of those problems where I can't solve the problem initially. I got to go through synthetic or long division to create a different version of the problem and then apply. So I'll do synthetic here. And now on the quiz, I'll give you a problem like this, where it's a nice and linear so that you can solve either using synthetic or long division. I think most students prefer synthetic. So I'll go through synthetic for this problem. Okay, so we'll work this out. Okay. So we want to solve for x. X plus 3 equals 0. X equals -3. So put the -3 outside your half box. Okay, we just want to list out the coefficients in descending order. Make sure that we don't skip any degrees. What's the first number we put? 2, then 5, and then good 0. So x cubed, x squared. We need a placeholder for degree 1. 0x. What's last? -12. Okay, any questions with the setup? Okay, what's the first thing we do after we create this half box and the number out in the front? Bring the 2 all the way down below the line. Multiply with your numeric value outside. -6. Add. Multiply. -3 times -1 is 3. Add. Multiply. And add. Now, initially, this was x cubed. I'm dividing by x, so what's going to happen? Degree will fall by 1. So this will be x squared, followed by x, followed by the constant, and this is what we call the what? remainder. So remainder, you put it over the divisor because you can't go any further. Okay, we don't want to leave this as the answer because we haven't done anything calculus related, but we've created a different version of the problem that is easier to handle. First three terms, I can just rely on what? Power rule. And the last one is a simple U substitution, which would just be natural log. So you can go through the whole natural log process here, but it'll just end up being 1 over x natural log, or 1 over be 21 natural log of x plus 3 plus c. Okay, so that's what's going to come out of this. Now, on the quiz, if you want to jump directly from here to here because you feel comfortable with that step, then you don't have to show me the whole U substitution. All right, let's go through each term here. 2x squared becomes cubed over 3. X becomes squared over 2. 3 becomes 3x, and then we'll hold on to that negative here. So minus 21 natural log of absolute value of x plus 3. And don't forget what at the end? Plus c. All right, you guys have homework tonight from 5.5.